Hello and welcome to another lecture of classical motion of a single particle. So, in this lecture we start a new topic, that is the topic of linear harmonic oscillations, okay, or simple harmonic oscillations. Now, there are several ways to describe the importance of such oscillations. One is, of course, you can see that whenever the force is proportional to the distance, and this is in general of the attractive sense. That means, if you take a force in 1D which is proportional to x, but which is exactly equal to some proportionality constant times x, where the constant is negative, or I can simply write this constant to be positive and I add a negative sign over here, then you know that the simple harmonic oscillation will be the resulting motion, because the Newton's second law will be m x double dot plus k x is equal to 0 for the system, okay, and you will have x is equal to now some a sin omega t plus phi, or you can sometimes say also, I mean, with equal freedom you can say a cos omega t plus phi, where this omega is given by root over k by m. Now, I want to introduce this simple harmonic oscillation from another point of view, that is that we already talked about central forces, and one very important result in central force was the Bertrand's theorem. Bertrand's theorem says that whenever you have a force field which is proportional to 1 over r square or force field proportional to r, then you will have some very privileged situation. That means, every bounded motion will have a closed trajectory. That is the guarantee, okay, for these two force laws. This one is called the inverse square law, which we already discussed, and this one we discuss today, okay, or rather the discussion is going to be started from today. Now, although we know that this is simply a case where you can write this force law to be proportional to r, and actually you can write the whole force to be f of r cap, and that will be some minus k r cap, okay. Now, finally, when you write this, basically that gives me k times r vector, and then although this is central force, for this specific structure I have something very interesting, and I can write, for if I, instead of writing in polar coordinates, if I write this in general 3D coordinates, or also, although I know that in the framework of central force only the motion takes place in a plane, you can also write it in the like 2D coordinates, but even in the 3D coordinates, if you simply write this, okay, you can write m x double dot is equal to minus k x, m y double dot is equal to minus k y, and m z double dot is equal to minus k z. And since all these three directions are mutually independent of each other and the equations of dynamics are not coupled, then if you just find the solution for 1D, actually in the similar way you can find the solution for the other directions, okay. Now, it is you to think and tell me that whether under such cases I have to really go for a 2D motion or a 3D motion, okay. But whatever, at least we can say that at least we can try to solve this equation, and whether finally this will be 2D or 3D, it will not change much, because the same solution will be repeated in the other directions, whether this is 2D or 3D does not matter, okay. Now, before even coming to that, I am telling you another importance of this type of force, and as I already discussed about this point in some of the previous lectures, that whenever a particle is under some central force or some potential, let us say in 1D, okay, and the particle is moved a little bit or perturbed a little bit from its some position of equilibrium. If the position, initial position of equilibrium is a stable position of equilibrium, then if you perturb it by a very weak amount, by a very small amount, you will see that this particle will exhibit a simple harmonic motion. Okay? That is another very important aspect of simple harmonic oscillators. So, I can directly start from this equation and I can say, if I solve this, because finally the main goal of classical mechanics is to solve for x t and x dot t. Okay. So, then I am done. So, already I know that if I have a relation like this, either by using trial solutions of type trigonometric or by using the constant of motion, which is for 1D, if you remember, that also was discussed in a lecture, half m x dot square plus half k x square. This is the total energy, total mechanical energy in 1D. If this is a conserved quantity, and we know this is a conserved quantity here, okay, then I mean for at least for 1D case this is conserved quantity. For 3D cases there is a certain thing you can always write that. So, just from this equation you can easily show that this is a conserved quantity. Okay. Here for 3D or 2D, once again this is a question, but what you can say that the energy total will simply be half m x dot square plus y dot square plus z dot square plus k by 2 x square plus y square plus z square. Okay. Or if you want for 2D, E total, if I just think that this is a central force and the motion takes place in a plane, let us say xy plane, then it is half m x dot square plus y dot square plus k by 2 x square plus y square, and this is the conserved quantity. And so, you see that this quantity is separately conserved and also this quantity is separately conserved. Here I can write it as x and ey, and both of them are separately conserved, and that is why this E total, which is the sum of Ex and Ey, that is also conserved. Okay. From this equation this is pretty easy to show that. Now, if we know this is conserved, then for 1D motion I can actually also solve this and find the trigonometric solution of type. So, I just write this is the equation x double dot plus omega square x is equal to 0, where omega is equal to root over k by m. Then I can actually write the complete solution for this equation is equal to, once again just for reminder, this k is the force constant and m is the mass of the particle. Okay. So, x will be given by some constant c cos omega t minus phi 0. That is the form in general we can write for some for a arbitrary 1D simple harmonic oscillator. Okay. And now I will just tell you what they are exactly, the vocabulary, some vocabulary. So, this is the displacement, this is the amplitude, this is called the frequency, this is time, of course you know, that is the independent variable over here, and this is called the initial phase or epoch. Okay. So, this is all about the vocabularies, and you know that this is finally this is the amplitude, and that gives me the measure of the maximum possible displacement. Omega is the actually we say frequency, but this is actually angular frequency. So, omega is nothing but 2 pi f, where f is the true frequency, and it simply says that how many times oscillator oscillates completely in a unit interval. So, for example, if I give you 1 second time, then how many times the oscillator performs a complete oscillation. Okay. And if you multiply this by 2 pi, you will have omega. Okay. Now, I can simply start with this formula, that this is the solution I can obtain in various ways, and using that what I can do. Now, this is a solution which is involving different constants, okay, which came as a result of integrations, as we all know, and now we have to somehow use some information which we know and to relate them to this constants. So, let us say the initial condition which we know is that, let us say the oscillator had some initial displacement x 0. So, x 0 is nothing but x at t is equal to 0, and at t is equal to 0 its velocity or x dot was v 0. If we have this assumption, then what to do? I can simply write that okay, when t is equal to 0, then so at t is equal to 0, c cos phi 0, because cos of minus phi 0 is equal to cos phi 0 is equal to x 0, and we can also write an x dot from here which is equal to minus c omega sin omega t minus phi 0. So, if c cos phi is equal to x 0 and c sin phi 0, which comes when I make this one, when I evaluate this one at t is equal to 0, you will have sin of minus phi 0, which is minus sin phi 0, with a minus sign here, it will give you simply c sin phi 0 times omega, which will be then your x dot at t is equal to 0, then you will have this is equal to v 0. And simply from that you just try to utilize the sin square theta plus cos square theta is equal to 1 type of identity, which gives you simply c square is equal to x 0 square plus v 0 square by omega square. Okay. This is very interesting. I can immediately also calculate another things. If I say that my total mechanical energy is equal to half m x dot square plus half k x square, which is constant. So, this will be actually constant throughout the motion, and that is why the value of E at t is equal to 0 will be the value of E throughout. Okay. And that is why I can also write this is exactly equal to half m v 0 square plus half k x 0 square. And then I am taking this, I just take m by 2 over here, so that I have v 0 square plus k by m x 0 square. Okay. I think I have not done any mistake, yes, and this is again this is omega square. Okay. So, I have another relation which I can write immediately here, that is E is equal to m by 2 v 0 square plus omega square x 0 square. Okay. Now, we know c square is equal to x 0 square plus v 0 square by omega square. So, I can actually write something here. So, if you just tell me whether you agree with me or not, that x then I can write as c, which is then I can easily write c square, which is now this 1 over omega square x 0 square plus v 0 square. Okay, that I can write here, and you can take this v 0 square plus omega 0 x 0 square to be 2 e by m. So, that will be actually 2 E by m omega square, right. So, this will be 2 E by m, yeah, and finally, you will have 2 E by m omega 0 square, m omega square, sorry, m omega square cos omega t minus phi 0. You can also write this thing exactly in the form of this. So, since this was c, this is also equal to root over x 0 square plus v 0 square by omega square. Okay. There is a, I think I have made a mistake over here. So, this is c square, yeah. So, here it will be simply root over this, yeah, yeah. So, this is a root over of this, yeah. Now, what about this phi 0? May I do something interesting also with the phi 0? This is super easy, because you know that I use a green one here. Cos phi 0 is equal to x 0, I mean c cos phi 0 is equal to x 0 and c sin phi 0 is equal to v 0 by omega. So, then what will be tan phi 0? It will simply be v 0 by omega x 0. Okay. So, you can simply write phi 0 is equal to tan inverse or arc tangent v 0 over x 0 omega. So, here you can write v 0 over x 0 omega arc tangent. Okay. So, just using the initial conditions or initial values of the displacement and the velocity, you can also do this, right. And now, I am trying to do something also interesting, that is, if you have this, then the solution, the complete solution is, I am simply writing this, I can write somehow in terms of x 0 and v 0, so that it looks a little bit homogeneous, okay. Root x 0 square plus v 0 square by omega square times cos omega t minus, should use this one, yeah, minus tan inverse v 0 by omega x 0. Okay. This is the complete solution for 1D simple harmonic oscillation, okay, with x 0 and v 0 to be the initial displacement and velocities respectively. Now, I want to also calculate a little bit, I mean another simplified expression for the total energy. So, the total energy I have already said that this is nothing but half mx dot square plus half kx square in 1D of course, and then I am just trying to write directly the solution. So, x is equal to c cos omega t minus phi 0 and x dot is equal to minus c omega sin omega t minus phi 0. I just take the square of those things and I will have half m. So, c square omega square sin square omega t minus phi 0 plus half k c square cos square omega t minus phi 0. Now, I can say that omega square is equal to k by m. So, I can actually say that k is equal to m omega square as well. So, I can now write half m omega square c square sin square omega t minus phi 0 plus half, instead of k I write m omega square. So, it will be m omega square c square cos square omega t minus phi 0, which is exactly equal to again sin square this plus cos square this will be 1. So, you will have half m omega square c square, and then you can actually write half m omega square. What was c square? x0 square plus v0 square by omega square, x0 square plus v0 square by omega square, and that is exactly you can write here, x0 square plus v0 square plus omega square is equal to 2e by m omega square. So, that is exactly what we got here as well. So, this is a way to cross check just by directly putting the exact solutions of the motion. Okay. Now, how should be the plot of a simple harmonic oscillator's motion in x versus x dot plot? That means, I give you a plot where along the x axis the displacement is plotted and along the y axis the x dot or the velocity is plotted in 1D of course. So, you see, if you remember this equation, the equation is actually this. The relation, so I am here trying to plot the trajectory of the motion of a simple harmonic oscillator in x dot plot, and that is why I am simply writing this constraint which relates x dot and x, and I can say that the correct way of writing this in a compact way, you can write half m x dot square plus half k x square is equal to E, and x dot square, if I now take this x square and then I do something like this, you will see that would be much more easier to understand, is equal to 2E by m, because what I did here, I just multiplied everything by 2 by m, and then that is why this gives x dot square plus omega square x square is equal to 2E by m, and omega square is nothing but k by m. Okay. And if you do that, you actually have x dot square by root 2E by m whole square plus x square by 1 over omega root 2E by m whole square. So, you see, and that will be equal to 1. So, in a plane having the x axis representing the displacement and y axis representing the x dot, what you can actually expect the trajectory will be? This will simply be an ellipse. Now, which one will be the bigger one? So, of course, you understand that there is a 1 by omega factor. So, if omega greater than 1, that means root k is greater than root m, right, and then a by b. So, a by b will simply be, if I just assume this one as I would say this one as my a, I can actually do the other way around. Yes, right, this one is my a and this one is my b. So, I can actually say this is b because x dot is along y axis, and so this is actually b square and this is a square. Okay. So, you will see that whenever I have this condition, then a by b will simply be 1 over omega, right, and if I have this, then that will be less than 1 over omega, of course, yeah, less than 1, and then a would be less than b. So, your thing will be, so for x dot you will have b which will be now greater. So, your ellipse will look like this. It is a bad ellipse of course, but it should look like this. On the other hand, if your omega is less than 1, then your A will be greater than B and you will have an ellipse which looks like this. Okay. And you will also understand that when for a given system E is conserved, that gives me an ellipse of this, okay, because E is finally gives me this whole thing, and if E changes, let us say E increases, both A and B will increase. So, you will have larger ellipses. If E decreases, you will have smaller ellipses. The same thing acts also here for this type of ellipse. If E decreases, you will have smaller ellipses, and if E increases, you will have larger ellipses by having the same configuration. Okay. So, you see here in this lecture what we have learned is how to solve exactly the equation of one dimensional simple harmonic oscillator and connect them to the basic constants of motion, and finally, how the trajectory looks like, I mean how the motion of a simple harmonic oscillator looks like in a diagram where displacement is plotted along x direction and the velocity is plotted along the y direction, and this type of diagram which we will learn later is called the phase space diagram. Thank you.